Whew, all right, so here we are, punching the time clock, back to the grind. Um, Doing homework these days is maybe feeling like our 9 to 5, and I know in the moment it may feel like a thankless, low-paying job, but I assure you, I promise you, payday is coming. It's coming soon. Payday, of course, is going to be the day that we take our test and our final exam. And while it's true, we may not get paid in millions of dollars, we are going to get paid in 100%. And that, to me, feels even better than $1 million. All right, so we're really kind of doing everything we did in 7.1 all over again. Yeah, I know. It sounds like fun. All the problems in 7.1 involve normal distributions. So when we're working with normal distributions, we used two functions. Mostly we use the normal CDF function to find probabilities. Occasionally we use that inverse norm function to find percentiles. And remember, right, we always had at the end of those functions, we had to put in the mean and the standard deviation. In 7.1, we were always putting in zeros and ones. In 7.2, we're working with situations where the mean is not necessarily 0 or 1. So the only tweak, the only extra wrinkle, the only additional complexity is instead of 0 and 1, we're going to put, say, well, looking at the slide right here, we're going to put 20 for the mean and 4 for the standard deviation instead of 0 for the mean and 1 for the standard deviation. I mean, you might argue that the kind of additional extra wrinkle is that this type of problem is more amenable to word problems. So, right, we're going to see a lot more word problems in 7.2 versus 7.1. But really, in terms of how we solve these word problems, it's really everything we already did in 7.1. And if we put in the time to 7.1, then this should be like no big deal at all in BD. So here's problem. This is the problem we're going to start with 17a from page 316. Right, this is the book's phrasing. It says a normal population has a mean of 20 and a standard deviation of 4. As of now, it's still a little generic. So again, just think of this as some test. On average, people can get a 20. There's a certain amount of variation. Not everyone gets the same score. It turns out we can quantify or measure that variation by saying it has a standard deviation of 4. And we want to know what proportion of the population, sort of what percentage of all students end up scoring in 18 or less. So yeah, there it is, right? We have something that's normal. We want to know what's the probability of being less than 18. So again, a picture's still our best friend. I drew that picture. Instead of being centered at 0, it's instead centered at 20. 18 is to the left of 20, and I want the area, right, the proportion, the probability, to the left of that thing. Oh dear, I just noticed a typo. So so that should be normal CDF. I apologize for this typo that I'm seeing now for the first time. Should be negative 1 e to the 99. And then 18, and then 20 and 4. And we plug all that into our calculator, we get 0.3085. I'm going to see if I could fix that typo. So you may be still looking at it and saying, like, what typo? But when I was narrating, there was a typo. I'll see if I can fix it without having to re-narrate this entire thing. And here's an example of larger than. So this just says, okay, same mean, same standard deviation. What's the probability that a randomly chosen value will be greater than 25? The answer is, oh man, there's another typo. Normal CDF, 25, 1e to the 99, that's perfectly fine. And then the mean is 20. The standard deviation should be 4. Not looking good for my typing. I apologize. Hopefully you're a little bit better at it than I am. I'll double check, but I do think that the answer looks correct to me. So I'll make sure I verify. And do I believe that's correct? No, I don't think that answer is correct. So make sure you put a 4 in there and you're going to get a different answer. And I'll see if I could change that also. I apologize. But it should be 25, 1 e to the 99, 20, and 4. Maybe life is humbling me for saying how easy these problems are. Maybe we just proved that you may or may not need it, but apparently I need the extra practice. So actually, problems 18, 19, and I think 20 are all the same type of problem. So why don't you pause this now? Then why don't you go ahead, if you haven't already, solve those problems, then come back and take a look at the rest of the PowerPoints, and I'll double check and make sure that there's not typos in the rest of the stuff. All right, so here we are, 18A. I'm kind of skimming the book as I'm reading this to make sure everything looks right to me. Yeah, I think it looks like I got all the mistakes out of my system. Looking really quick, everything looks good to me. If you do notice any PowerPoints, certainly when you're typing and cut and pasting and doing like these things by bulk, and if you're listening to Marshmallow YouTube videos while you're doing it, it's definitely easy to make some mistakes. So feel free to call me out on it if you see any mistakes there. But I believe that's 18, 19, and 20 for your perusal and double checking. 21, I mean, it's a little bit of a wrinkle, but again, not a wrinkle that we haven't already seen before. Now we want to know the probability of being between two numbers. Again, with our calculator, the between two numbers is actually easier. But yeah, that's right. The problems are actually getting easier, not harder. We have a normal distribution. It's centered at 47, so I draw that thing. All right, the mean, the peak is at 47. Standard deviation of 3. I want the area between 40 and 50. Throw that all in my calculator. I get about 83%. And then 21B, what's the probability we're between 50 and 55? So again, plug in the same numbers. Looks like I got the mean and the standard deviation correct there. And then I think 22 is going to be the same type of problem. So again, pause it, solve that problem on your own, and go ahead and double check the answers. And there you are, 23.56% and 46.8%. Yeah, pretty easy, right? All right, let's move to the next type of problem. So here we're told we have a normal population and we want to find percentiles, right? So again, it's kind of that opposite problem. Before we were given some value and we wanted to find the probability. Here we're given the probability, we want to find some value, right? That's that little question mark at the bottom. So if we have a normal population with a mean of 12 and a standard deviation of 3, what's the 40th percentile? We could find percentiles using the inverse norm function, right? The syntax is PMS, percentile, mean, standard deviation. So inverse norm, 0.4, 12, and 3 gives us 11.24, right? So it's saying that that question mark should be 11.24, which is basically saying, right, if we're thinking of this again as like a test with a mean of 12, right, what's the value such that 40% of the class scored less than it? That value is 11.24. All right. Again, what follows after this is 2 or 3 percentile problems. So I want you to pause it if you haven't done it already. Right, go ahead, do those problems, write down your answers, then unpause this and take a look at the answers. There we are, 85th percentile, 64.29. 19th percentile, 38.10. 91st percentile, 115.24. All right, and then this is sort of the last escalation of complexity. We're doing all the types of problems we've done before. Less than some number, more than some number, between two numbers. Find me some percentiles. That's the only type of problem that we're going to be doing for the next, I guess, 15, 16 slides. The only maybe slight little extra wrinkle is that these are all dressed up. These are all wrapped up and word problems. So we're going to have to take the word problem and translate it into the correct sort of calculator nomenclature. Not that hard to do though, as you'll see. So I mean, it's still pretty explicit, right? But I mean, to me, the word problems are more interesting because to me, the word problems are actually starting to show me that all this stuff that I'm putting the time into, that all this stuff I'm putting this time into, this 9 to 5 that we were talking about, actually has some really interesting uses in real life settings. I mean, it's not surprising. Go on I don't know, what do you go on Indeed, go on Glassdoor, maybe go on LinkedIn, start googling jobs with the word statistician in it, and there's your payday right there. Right? We learn statistics because statistics is useful. We learn statistics because statistics solves real life problems. And if you want to get paid, doing something fun, well, maybe it's time to start thinking about changing your major. If you want to learn more about changing your major, send an email to smcclintock@wcupa.edu, and I'll tell you everything that you need to do, and I will help make all your wild statistical dreams come true. I promise. Yeah, but until we get that wonderful, fun, high-paying job, we gotta put in the work. We gotta do our homework problem. So let's stop fantasizing for now and get back to that. Right? What's the probability someone's blood pressure is less than 70? Well, that's the syntax listed in A. What's the probability that someone's blood pressure is between 75 and 90? That's 54%. What's the probability someone's blood pressure is more than 90? That's the 16, close to 17%. Probability someone's blood pressure is less than 65. That's going to be our 5.87%. Now, notice for part D, the book actually asks the question, is it unusual for a woman to have blood pressure lower than 65? The book asks a lot of questions like that. Is it unusual? Is it unusual? Is it unusual? Their definition of unusual is 5% or less. So, right, part D, they say, is it unusual for a woman's blood pressure to be less than 65? That probability is a little bit more than 5%. So we would say that it's not unusual, although it's pretty darn close to what our book would call unusual. Now again, I know I didn't write out the entire problem. It would have bloated the PowerPoints if I did that. Instead of like 25 slides, it'd be like 50, 60 slides. So, I mean, presumably you've worked on these already. Presumably you've read these already. Presumably you have access to write some copy or some version of the book. And so I tried to kind of keep these things a little bit slimmed down, and hopefully that works for you. Now also notice like the book kind of like skips things. So like problem 27 is about blood pressure, but if you look through the things, problem 29 is also about blood pressure. So I think on the next slide I skip from 27 to 29, which seems a little weird, but it just keeps us within the same context, keeps us still within the same type of word problem. Yeah, there it is, 29, more blood pressure. So right here, it's just asking for percentiles, 30th percentile, 67th percentile. It asks us to find the third quartile, but remember from, I guess maybe chapter 2, the third quartile is the 75th percentile. So that just means plug 0.75 in there. Yeah, I know. Piece of cake, right? So let's move backwards now to 28 and a different context, different type of word problem. Aw, I love babies. They're adorable. So right here, we're just working with baby weights. What's the probability that a baby is going to weigh more than 13 pounds, less than 15 pounds, and so on and so forth? Right, there's all the answers for you to double check. Number 30 is looking at percentiles of baby weights. That's actually something that people do talk about, right? You have your cute little adorable baby, and they say something like, "Oh, your baby's in." Well, if we're talking about say C, maybe your baby's like a little princess. Maybe she's particularly dainty, and they say like, "Oh, she's in the 25th percentile." What does that mean? It means that 25% of all babies have weight the same or less than your baby. And if we want to find out what that 25th percentile is, we can use our handy high-powered statistical calculator, the inverse norm function, and so that's 9.68. So 9.68 is the value such that 25% of all babies weigh that much or less. Yeah, let's go fishing, right? Like a little virtual field trip to to lake statistics or lake normal distribution or whatever you want to call it. All right, hope you brought your tackle box with you. So here we're looking at fish. We want to know probability of getting fish that are certain lengths. So here, probability of fish is less than 450 millimeters, sorry, between 400 and 500 millimeters, and less than 400 millimeters. And again, if you caught a fish less than 400 millimeters, right, that would be very small. So again, why do we care? Well, maybe it helps us like figure out the length, right? A lot of lakes have a rule: if you catch a fish below a certain weight or below a certain length, you have to throw it back, right? So it has time to kind of grow larger. And so maybe like some kind of calculations or probabilities like this would help us, or help, say, the Fish and Wildlife Commission sort of determine kind of what are these thresholds that we should be using for when we can keep a fish and when we might be able to throw one back. And then here's some percentile problems. So right, we go ahead and find different percentiles. I think that C is finding the quartile. Oh, and then actually D, it looks like D is exactly the type of problem I was talking about. So D actually says, hey, we want to put a size limit on fish, and essentially we want it to be that 15% of fish that are caught get thrown back. So this is almost like putting like a little threshold or a restriction on like how frustrated we're gonna be, because it is frustrating. You catch a fish, you're all excited, you're like, man, I'm gonna take this home and grill it all up, make some kind of I don't know, whatever people do with fish, some kind of like fish stew or fish puree, or maybe like a fish smoothie or something. But then you measure it and you weigh it and you're like, it's too small, I gotta throw it back there, and all your visions of fish smoothies kind of, right, are kind of dashed with it. So if we only want this kind of sad situation to happen 15% of the time, well, right, we could set that limit to be 438.51, right? So if we make a rule that if a fish is has a length less than 438.51, we throw it back. Otherwise, we keep it. We're only going to be throwing fish back 15% of the time, but it's going to keep 15% of the fish's population. At the same time, it's going to keep 15% of the fish's population sort of protected. And maybe that's kind of like a critical number for like fish to be able to breed successfully and kind of keep creating fish. Maybe a sad thought for a continued recreational amusement. And then, right, as if yeah, a lot of butchering of animals and eating them examples. So we're done with fish. Now let's it's kind of like we're done with breakfast. Let's move on to lunch. So let's think about some nice, delicious fried chicken. Um, what's the probability of chickens between 1100 and 1200? Looks like the units are grams. Probability it's more than 1500 grams. And then C is probability of being more than 1500, no, 1550. And then it asks, is that unusual? Turns out, right, almost 16% of all chickens are that big. So that's not less than 5%. So we would say it's not necessarily unusual. And then it asks us for some percentiles. D is actually a pretty interesting one. I've seen problems similar to D on our comprehensive final exam, actually. It's a little bit similar to that fish one, right? Like you're actually you want to kind of offer like a money back guarantee, but you don't want people cashing in on it very often. So again, you could actually, right, if you kind of know statistics, right, and you're a business person, you could actually set your own threshold. So I mean, rather than just making up a number out of thin air, you could have a very sort of quantifiably justified number in terms of like your money back guarantee. So part D is basically saying like you want to only give people their money back 1% of the time, right? You get someone buys a chicken and the chicken's a little too scrawny, you want to give them their money back, and you can dictate like I only want to this a certain amount of time. Let's say 1% of the time. If that's what you want, then your money back guarantee should basically be 1,012.48 pounds. Anytime a chicken weighs less than that, they get their money back. Anytime the chicken's more than that, well, buyer beware. So if we stick with that strict rule, only 1% of the time we'll be refunding people their money. And right, so another problem, right? I mean, at this point, you should be able to just pause this and just boom, 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 knock out all the problems. I think they're all just this type of problem. Moving on for the next however many 7-ish slides that there is. But the radon problem, I think the radon problem is kind of cool. It's kind of shows us. It's good like from a diagnostic perspective as well. So here we're sort of like we're using a radon detector to like almost like diagnose our home. But like the same sort of rationale also holds true for us when we go to see like a doctor, for example. So here we're like measuring radon. It's kind of interesting problem because it's sort of like saying like so at normal CDF we're plugging in 4.1 for the mean. So 4.1 is actually like an unhealthy amount of radon. But we could potentially, it turns out, misconclude that everything's fine. So if we buy like a cheap radon detector that sort of has the specifications kind of laid out in the problem, and if basically we're saying if that radon detector tells us it's anything less than 4, then we're fine. Then there's about a 30% chance, so close to like a 1/3 chance that that if the radon is at this dangerous 4.1 level, that we still might, in this case, misconclude that everything's fine. So yeah, so maybe this is a nice example to highlight. Maybe we don't want to buy cheap radon detectors. Because then it talks about like a different way of detecting radon, a more involved test. This one essentially is like the same in every way, except it has a smaller standard deviation. So this is really illustrating the power of the standard deviation, or in the kind of context that we're talking about, we might call this really the precision of the test. That's smaller the standard deviation, the more precise that test really is. And so here, if we really have a dangerous level of radon, if we really have a 4.1, if the mean really is 4.1, now there's a less than 1% chance, admittedly still possible, that we would detect or that we would misconclude that there is a safe level of radon right in our basement. So kind of I think a nice kind of interesting real life example, and certainly worth thinking about. I mean, anytime like doctors or nurses are right testing our blood and whatever it else that is that we give to them to test, right, they're being applied to diagnostic procedures which also are potentially imperfect. So right, at the end of the day, misdiagnosis is always a possibility, and that's why, right, I mean, a really interesting statistical problem is being able to test for any tool or any process how sort of accurate or precise it really is. And of course, our goal should be to use tests that are as accurate and precise as possible. All right, so more radon problems. They throw maybe a little bit of a curveball to us with C when they say find the median of the measurements. But remember, median's just the 50th percentile. And remember, 50th percentile for normal distribution is its mean. That was like one of our facts long ago. So we don't even really, I mean, you can plug it into your calculator as inverse norm, 0.5, 4.1, 0.2, but you really shouldn't need to. Anytime I ask you what the median is for a normal distribution, you should just be writing down it's the same as the mean. And in this case, we said the mean is 4.1. All right, so I mean, at this point, it's just the same type of problem over and over. If you haven't already, I'm just going to encourage you to pause it and solve the remaining problems. Not too many left at this point. And then we'll just kind of go through the slides. I'll just kind of sit here quietly while you compare your answers to mine. Looks like they threw that same median curveball at us for part C. This time I didn't even bother putting it in the calculator. I said, hey, we should be able to just know without using the calculator. It's $110.14. And tires. Yeah, I guess tires, because at this point, after doing so many problems, we're kind of tired, aren't we? Ha. Still tired. Just 2 more slides to go. So if I'm looking here, I don't remember. Is it going to be tree heights? I don't know. Let's find out. Ah, there it is. Heights of trees. If you look at the textbook, there's this really pretty picture of a cherry tree. Yeah, makes me pine for being outdoors. Looks like I put a little something there. Oh, yeah, so 42 part D says they want to study the tallest 1%. So again, right, the extra little step we got to take is that the top 1%, hopefully at this point we can kind of see that that corresponds to the 99th percentile. 99th percentile is a value such that 99% is less than it, but the flip side of that is that 1% is to the right of it. So when they say top 1%, they're asking for the 99th percentile. So again, we just plug inverse norm, 0.99, and we did it. So congratulations. We've earned ourselves a nap. We've earned ourselves a little bit of outdoor time. Oh, maybe we can go to Longwood Gardens. How picturesque would that be? And you've earned yourself some money. And by money, I mean 100% on the next test. So I'm looking forward to being there and helping to hand out your paycheck.